Hello there, and welcome to the Sleepy Science Channel. Tonight, we are heading into the science behind one of the most beautiful sights on Earth, the Northern Lights. High above the world, rivers of color drift across the sky, glowing in silence. They twist and shimmer like living spirits of light, turning the darkness into something almost alive. For centuries, people have watched in awe as green, red, and violet waves flicker over frozen lands, never knowing exactly what force was at play. Somewhere beyond our atmosphere, a story unfolds between Earth and the Sun, a dance of charged particles and magnetic fields that turns invisible energy into radiant color. The aurora is more than just lights in the sky. It is a natural and scientific marvel, where the breath of a star brushes against the edge of our planet and leaves the air glowing with quiet wonder. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your eyes grow heavy and picture the night sky unfolding around you. Let's begin. The northern lights are caused by solar energy striking our night sky. High above the clouds, a blanket of atoms and molecules lay silently in wait. Into this layer, charged particles arrive from space and plunge into the upper atmosphere. They collide with oxygen and nitrogen and share their energy like a spark passed from one hand to another. The atoms leap to excited states, then fall back and release that borrowed energy as light. What we see from valleys and ice fields is the afterglow of countless microscopic meetings, each one a tiny lantern turning on for the briefest moment. The sky becomes a tapestry woven from quantum steps that play out invisibly until the final note appears as color. The spectacle is vast, but its heart is intimate, an exchange measured one particle at a time. When these encounters blossom across the night, the heavens feel close enough to touch, and the familiar world takes on a secret inner brightness. Each color in the aurora comes from a different atom lighting up the sky. Every hue is a signature, a quiet autograph left by a specific ingredient in the air. Oxygen writes in greens and reds with lines that belong to its own inner architecture. Nitrogen prefers purples and blues, its molecular bands brushing the darkness with a cooler glow. The atmosphere is not a single canvas, but a layered gallery, and every level hosts its own palette. As energy arrives from space, the rules of atomic structure decide which shades can appear, which transitions are permitted, and which are too shy to shine. In the stillness above mountain peaks and frozen lakes, this chemistry becomes choreography. Colors emerge in drifting arcs, then fade as atoms relax and return to rest. The eye follows, not knowing that each tone is a clue, a map to who is glowing and where in the sky that glow is born. The night becomes both mystery and answer. The green glow is oxygen shining 100 kilometers above Earth. At this lofty height, the air is thin enough that excited atoms can hold their light for a lingering moment before collisions silence them. In that pause, the emerald note appears and spreads along long ribbons that sweep from horizon to horizon. Green gathers along gentle arcs, then spills outward into wavering curtains that seem to breathe with the planet. Human vision is especially sensitive to this hue in low light, so the eye catches it first, following its soft edges as they curl and twist. The scene feels alive because it is the sum of many tiny acts, each oxygen atom lifting its voice in the same tone, then falling quiet again. The ground below remains dark and still, yet the sky hums with a slow, patient brightness that makes distant snow glow and rivers glint with hidden color. In that light, winter nights feel less cold, and the world seems quietly transformed. Red auroras appear when oxygen glows near the edge of space. Far above the green bands, where the air becomes almost nothing, oxygen can hold its excited state for a long breath before letting the light go. The result is a soft crimson that spreads like a veil, diffuse and weightless, hovering at the roof of the atmosphere. This red often crowns the display, a high halo that turns the night into a deep, otherworldly dusk. It moves more slowly and appears more ghost-like than the bright green lanes below, because collisions are rare in that rarefied height. Sometimes it pools near the horizon like distant embers. Sometimes it pours downward in delicate sheets that whisper of unreachable distances. To watch it is to feel altitude itself, the sensation of standing beneath an ocean of thin air that stretches into space. The red tells a story of solitude and patience, of light released only when the sky is quiet enough to let it be seen. Purple and blue streaks come from nitrogen molecules struck by electrons. Lower in the auroral theater, where air is thicker and motion is quick, molecular nitrogen flashes with cool tones that edge the green like frost on a leaf. These blues and purples often outline fast-moving structures, the racing fronts and sharp folds where energy pours into the atmosphere with urgency. Each molecule vibrates and rotates in its own patterns, turning collisions into brief, icy colors that flare and fade with a dancer's speed. The eye catches them as borders and highlights, as threads that stitch across the curtains and give them definition. They can arrange themselves into fine striations, then dissolve into mist as the energy source shifts. In their presence, the aurora feels layered and dimensional, with depth that can be sensed even from the ground. The cool hues hint at colder air and quicker lives, a realm where light appears and vanishes before the mind has finished naming it. Every aurora begins with a storm on the sun. Deep within the star, loops of magnetic tension tangle and build until they rearrange and fling charged particles into space. Sometimes the outflow is a steady wind, and sometimes it is a sudden surge, a vast gust that carries embedded magnetic fields across the solar system. When this breath reaches Earth, the meeting is not simple. The planet has its own magnetic shield, and the way the two fields lean and turn decides how easily energy can cross the boundary. If the invitation is open, power pours in, filling near-Earth space with restless plasma and setting the stage for light. Hours or even days after the solar unrest, night falls over the poles and the sky answers. The grandeur we witness is the echo of that faraway upheaval, transformed into color by air that would otherwise be invisible. In this way, a storm on a star becomes a painting above our heads. Earth's magnetic field guides charged particles toward the poles. Imagine lines of force arcing from southern high latitudes to northern high latitudes, invisible rails that curve through space. Charged particles spiral around these rails, bouncing between mirror points and sliding along the field until they find pathways that lead downward. Along those paths, they are funneled into narrow rings that circle the magnetic poles, not the geographic ones, and there they meet the atmosphere. This geometry explains why the lights prefer certain belts and why they can drift and shift when the field itself is stressed. The field acts both as shepherd and gatekeeper, allowing only particular motions and filtering particles by energy and pitch. To look at an aurora from afar is to see the field itself made visible, a living map projected onto the night. The poles are not simply places on a globe. They are where the planet's magnetic breath rises and falls, guiding travelers made of light. The northern and southern lights dance in perfect magnetic symmetry. When energy flows into near-Earth space, it threads along field lines that connect one hemisphere to the other. The result is a pair of auroral ovals, that answer each other across the planet, displays that often brighten, ripple, and fade in step. From above, they look like twin garlands circling the night caps, bound together by the same currents. Yet symmetry does not mean sameness. Subtle differences in the magnetic field, the season, and the direction of the arriving solar field can tilt and stretch one partner more than the other. Even so, a wave that rises in the north often has a companion in the south, separated by an entire world yet linked by a single magnetic thread. This mirror dance reveals the scale of the system, a reminder that auroras are not local lights but global sculptures drawn by forces that flow through the entire planet. Auroras are shaped by invisible magnetic field lines. Every arc traces an unseen path, aligned east to west and draped along the contours of the field. When those contours ripple, the curtains ripple. When they kink, folds appear. Plasma instabilities can braid the lights, pulling them into strands, then flatten them into sheets that slide across the sky. The shapes are not accidents, they are fingerprints of structure in near-Earth space. If one could paint those field lines with a brush, the strokes would match the forms that appear overhead. Even the sudden bright knots and beads that chase each other along a band are guided by these hidden tracks. The geometry lives above our weather, shifting with currents that circle the planet and flow down into the ionosphere. To watch the shapes change is to read a story about moving forces. The sky becomes a display window for physics that usually hides in equations and delicate instruments. The lights move quickly as electrons race along those lines. Bursts of energy ride waves in the plasma, and those waves can sling electrons downward with surprising efficiency. As the electrons plunge, they strike the thin air and leave trails of brightness that seem to run across the sky. The human eye reads this as motion, as if the light itself were a creature sprinting over the horizon. In truth, it is many individual impacts unfolding in a rapid sequence, each one adding a moment of glow before the next arrives. The result is speed that feels alive. Ribbons curl, edges lace with fine teeth, and sudden surges push fronts forward like wind on water. Even the quiet moments carry a hint of swiftness, a readiness to awaken into motion at the smallest change. When the pace quickens, it is as though the sky has found a new heartbeat, and the land below stands still to listen. When magnetic fields snap, they release bursts of light. Far beyond the reach of weather, magnetic energy coils and tightens in the stretched tail of Earth's magnetosphere. As the pressure builds, field lines begin to twist and reconnect, snapping into new shapes and flinging energy in every direction. The invisible event unfolds in silence, but its echo races toward the poles in torrents of charged particles. When those torrents reach the atmosphere, they ignite it like a match struck in slow motion. Curtains of light bloom, surge, and ripple outward as the stored tension of space unwinds into color. Each burst is the visible signature of magnetic reconnection, a process that powers storms on the sun and even explosions around black holes. For a few moments, the quiet sky becomes a canvas for one of nature's most profound exchanges, where geometry becomes energy and energy becomes light that flows like a living river above the frozen world. Some auroras are smooth curtains, others are crackling ribbons. The difference lies in how the energy arrives, how quickly and how focused the flow of particles becomes. When the influx is steady, broad sheets of light ripple gently, like silk catching a slow wind. When the storm grows restless and the plasma surges in narrow channels, the smoothness fractures. The aurora sharpens into thin, bright filaments that twist, braid, and crackle across the sky. These ribbons can dart and coil in moments, forming structures so delicate they seem drawn by invisible fingers. To the observer, It feels as if the atmosphere itself has texture, as if one could reach up and run a hand through the flowing light. Both forms tell part of the story, one serene and continuous, the other restless and electric. The contrast reveals how subtle changes in invisible currents can sculpt beauty out of chaos, shaping the same energy into many living forms. Auroras can shimmer 10 times per second during strong storms. At their most energetic, the lights no longer drift but flicker like breathless flame. Rapid pulses race through the plasma, creating waves that modulate the glow in quick, rhythmic flashes. To the eye, they appear as shimmering ripples, an almost musical vibration of brightness that comes and goes faster than conscious thought can follow. High-speed cameras reveal the truth. The aurora is pulsing in response to oscillations in the charged particles streaming down from space. Each flash is a heartbeat of interaction between sun and earth, a strobe of invisible power revealed as light. The experience of standing beneath such a display is unforgettable. The entire sky seems alive with thought, blinking in patterns that no one fully understands. It is a reminder that behind the tranquil beauty lies motion at impossible speed, a dialogue of electrons speaking a language made of rhythm and color. Astronauts watch the aurora from above like a glowing ocean. From orbit, the light does not hang above the horizon, but curls around the planet itself, a vast ring of emerald and violet that ripples across the upper atmosphere. To those aboard the International Space Station, the experience feels reversed. They look down upon the aurora, watching it rise from the night side of Earth like waves of luminescent tide. The arcs drift beneath them, rolling across continents and cloud tops, revealing the curved edge of the world in gentle silhouette. Sometimes the station even flies through the upper tendrils of the display, surrounded by faint light that seems to breathe with their movement. The view blurs the line between sky and space, between home and the cosmos beyond. To witness the aurora from above is to see our planet wearing a living crown, a reminder that the same beauty seen from the ground is part of something far larger and grander. A single aurora can stretch across thousands of kilometers. When viewed from space, the scale of the phenomenon becomes staggering. What seems from the ground like a distant arc above the horizon can in fact span from one edge of a continent to another. The glowing oval around each magnetic pole can widen until it encircles the world in a complete ring of light. This immensity arises because the energy that powers the display spreads through the entire magnetosphere, guiding particles along field lines that reach across half the planet. On clear winter nights in the far north, people separated by great distances may stand beneath the same luminous sheet, unaware that they are all watching different parts of a single structure. The aurora connects landscapes and cultures beneath one shared sky, a bridge of light that unites valleys, oceans, and mountains under a common wonder. Its true size defies imagination, stretching beyond the reach of any single human view. Cameras capture vivid purples and blues our eyes cannot see. The human eye is tuned for daylight, not for the faint radiance of upper air. At night, our vision loses sensitivity to the deepest blues and purples, leaving only the greens and reds visible. But cameras, especially digital sensors, can collect light patiently, gathering photons over seconds or even minutes until hidden colors emerge. Through the lens, the aurora blossoms with detail the eye never glimpses. Indigo edges, violet pillars, soft azure bands weaving among the greens. These unseen tones reveal layers of atmosphere and the energies that excite them, showing how complex the palette truly is. Long exposure images often look more surreal than real, but they are faithful records of wavelengths our senses ignore. When we look at those photographs later, we are seeing the world as it truly is, not just as we are built to see it, and the familiar night becomes astonishingly rich. The aurora is silent, even when it looks full of sound. Its forms move like music, rippling and crashing as though accompanied by some vast celestial orchestra, yet not a single note reaches the ground. The light is too far above for sound to travel through the thin air, so the spectacle unfolds in perfect quiet. Standing beneath it, the stillness can feel immense. The contrast between visual energy and audible emptiness so striking, it borders on surreal. Ancient watchers often imagined they could hear the light, translating its movements into whispers and songs to fill the void. The silence is part of its power, sharpening every breath and heartbeat until the viewer feels folded into the hush. The absence of sound lets the mind supply its own, a private symphony built from awe. In that quiet, the universe seems closer, speaking not with noise, but with the unspoken rhythm of light across the sky. Some people claim to hear faint crackles during strong storms. Reports come from Arctic travelers, researchers, and locals who swear that under certain intense displays, a soft rustling or snapping can be heard. The sound is subtle, like static on dry hair or leaves brushed by wind. For decades, scientists dismissed these accounts as imagination, since the aurora occurs too high for any sound to reach Earth. But recent experiments suggest that under the right conditions, charged particles can build up near the ground and discharge when the auroral field above shifts suddenly. If true, the air itself might produce an echo of the distant energy, translating the cosmic dance into delicate electric pops. Whether it is physics or perception, the idea adds another layer to the wonder, that something so far away might still find a way to whisper to those who watch, leaving the night filled not just with color, but with the ghost of a voice. Massive solar storms can make the aurora reach tropical skies. During extreme events, the boundaries of the auroral oval expand dramatically, pushing light far beyond the usual high latitudes. Records from history describe brilliant displays seen over regions that normally never witnessed them: islands, deserts, and cities near the equator. These rare nights transform the heavens into something no one expects, a northern phenomenon claiming the entire globe. The cause is an overwhelming surge of solar particles and magnetic disturbance that floods the magnetosphere and drives energy deep into lower atmospheric zones. When this happens, compasses twitch, radio signals falter, and the sky becomes alive with moving fire. To ancient observers, it seemed as if the world itself was aflame. Today, we understand the science, yet the sight remains just as startling. It reminds us that the boundaries of our planet's magnetic world are flexible, capable of reaching out and embracing even the warmest, farthest corners of Earth. Red auroras once looked like distant fires to ancient people. Before science could explain their origin, bright crimson glows spreading across the night were often mistaken for the reflection of massive blazes just beyond the horizon. Travelers and villagers would rush to warn neighbors of phantom conflagrations, only to find the forests untouched. The color carried emotional weight, a sign of blood, war, or divine anger in many cultures. Chroniclers wrote of skies that burned like furnaces and lights that heralded omens of great change. Even today, when we know the physics, that color still evokes a visceral response. It seems less like illumination and more like emotion written on the heavens. In those early misunderstandings lies a truth about the power of natural wonder. The same red that science now measures in nanometers once stirred fear and reverence in equal measure, showing that knowledge and awe can coexist, each deepening the meaning of the other. The word aurora means dawn, named for the Roman goddess of light. In Roman mythology, aurora was the radiant herald of morning, who opened the gates of day and swept color across the sky before the sun arose. Her name became the perfect metaphor for the luminous curtains that brighten the polar night, a second kind of dawn that arrives not with warmth, but with electricity from the sun itself. To ancient poets, she was renewal and hope, the world awakening from darkness. Scientists later borrowed her name for this celestial display, honoring both beauty and origin in a single word. The aurora truly is a dawn of another kind, where energy meets air and turns shadow into color. When the lights unfold across the Arctic night, they seem to echo that mythic gesture, pulling back the curtain of darkness and letting the edge of the cosmos shine softly upon the world once more. The Sami call the lights Vuosahas, meaning the light you can hear. Among the indigenous Sami people of northern Scandinavia, the aurora holds both reverence and caution. In their stories, the sky is alive with spirits, and the shimmering bands are said to carry sound, a faint whisper or crackle that only the most silent night reveals. To speak loudly beneath them, or to mock their movement, was once considered dangerous, for the lights could descend and carry away the disrespectful. Vuosahas is not just a name, it is a description of a living presence, an awareness of nature as animate and responsive. The idea of hearing the light blends poetry and experience into something uniquely human, a reminder that wonder often lives beyond measurable sense. Even today, when science explains the aurora in plasma and electrons, that older meaning lingers, asking us to listen more closely to what the universe might still be trying to say. Aurora colors depend on altitude, energy, and atmospheric gases. Each layer of the atmosphere has its own ingredients and pressures, and each reacts differently when struck by charged particles. High above, rarefied oxygen produces crimson veils, while lower oxygen glows in green, the hue most familiar to human eyes. Still deeper, nitrogen molecules yield purples and blues that edge the display like cool shadows at dawn. The brightness and blend of these tones depend on how fast and how powerfully the incoming electrons strike, how deep they penetrate before losing energy. Even the density of the air can alter the shade, muting one color while intensifying another. In this way, the aurora becomes a living diagram of physics written across the sky, an atmospheric rainbow powered not by sunlight, but by the breath of the solar wind. Each color is both data and dream, revealing the precise altitude where the Earth and cosmos meet in glowing equilibrium. Each color lasts only milliseconds before fading away. To the eye, the lights seem to drift lazily across the heavens, but beneath that calm is astonishing speed. Every point of brightness is born when an atom captures energy, glows briefly, then releases it as light before returning to rest. This process happens countless times each second, a cascade of flashes so rapid that our vision blends them into fluid motion. The aurora is not a single object moving across the sky. It is a constant renewal, an unbroken sequence of creation and fading that gives the illusion of continuity. In high-speed footage, one can glimpse the truth. Patches blink in and out, like stars appearing and vanishing behind thin clouds. The persistence of our eyes makes it seem whole, but the reality is fleeting. Each spark dies almost as soon as it is born, yet together they weave an eternal, shimmering river that never seems to end. The same forces that make auroras can disrupt satellites. The energy that paints the polar skies does not stop at beauty. When magnetic storms surge through near-Earth space, they fill the upper atmosphere with charged particles that can bombard satellites and spacecraft. Electronic systems designed for calm conditions suddenly face torrents of radiation that flip bits in memory, overload circuits, or even push satellites off course by swelling the outer atmosphere with heat. Engineers must shield delicate instruments and build in fail-safes to survive these cosmic tempests. During intense storms, satellite operators sometimes power down components or shift orbits to ride out the disturbance. The same invisible current that lights the poles can scramble signals, distort navigation, and turn precision tools into unreliable ghosts. It is a reminder that nature's elegance is inseparable from its power, and that every shimmer of light in the night sky carries both wonder and warning for those who reach into space. Power grids can hum when auroral currents surge through Earth. Beneath the magnetic storm's beauty lies an unseen consequence: vast electric fields induced across the ground itself. As geomagnetic forces change, they generate currents that flow through conductive materials, including the metal veins of modern civilization. Transmission lines stretch for hundreds of kilometers, forming unintended antennas that collect this slow-moving electricity. During strong auroral events, transformers may vibrate audibly, their cores resonating with the extra flow, while protection systems struggle to balance the sudden surges. In extreme cases, equipment overheats and circuits fail, leading to regional blackouts that can last for hours or days. To many who live under those lights, the faint hum in the power grid becomes an eerie echo of the glowing sky above. The same energy that creates beauty in the heavens can sing through the bones of the Earth, a physical reminder that the planet and its technology are part of one connected system. Satellites warn us when geomagnetic storms are coming. Orbiting observatories constantly watch the sun, measuring its flares and tracking bursts of plasma as they race outward through the solar wind. Instruments detect changes in magnetic polarity, particle density, and speed, translating those distant eruptions into early warnings. When a solar storm is directed toward Earth, the data travels across networks in minutes, allowing scientists to forecast when the impact will arrive. Agencies around the world release alerts to airlines, power operators, and communication systems so they can prepare. These space weather forecasts have become a quiet safeguard for modern life, turning what was once unpredictable into something we can at least anticipate. The watchers themselves orbit within the same magnetic environment they study, their sensors feeling the first touch of the incoming wave. Thanks to them, the silent dance of light no longer arrives as a surprise, but as a story that unfolds with understanding and awe. Solar eruptions can double the size of the auroral oval overnight. The glowing rings around each pole expand and contract with the pulse of solar activity, sometimes growing so vast they engulf latitudes far beyond their normal range. When a massive coronal mass ejection from the sun slams into Earth's magnetic field, it floods near space with charged particles that spread the aurora outward in a single surge. Entire continents that rarely see the lights suddenly find themselves beneath pale green veils. To observers, it feels as if the planet has grown a new atmosphere of color overnight. Scientists track these expansions using satellites that map ultraviolet emissions from above, watching the ovals swell like living organisms responding to an invisible tide. Each expansion is both breathtaking and scientifically valuable, revealing how flexible the magnetic boundary can be when touched by the sun's force. The spectacle reminds us that Earth is not static, but a responsive participant in cosmic weather. The auroral oval expands and contracts like a living heartbeat. At any moment, the lights trace a ring-shaped zone encircling each magnetic pole, shifting constantly with the rhythm of space weather. When solar wind pressure increases, the oval stretches outward. When it relaxes, the ring tightens back toward the pole. This pulsation can occur on timescales from minutes to hours, creating a slow breathing pattern that mirrors the balance between Earth and Sun. Satellite imagery shows the ring glowing brighter during substorms, then dimming as energy disperses. For scientists, these cycles reveal how charged particles circulate through the magnetosphere. how power flows along magnetic field lines, and how our planet maintains equilibrium amid solar turbulence. To anyone watching from the ground, the motion feels alive, as if the world itself were inhaling light and exhaling darkness. The auroral oval is not fixed. It beats with the same quiet persistence that animates every living system under the sky. Auroras follow magnetic latitude, not geographic latitude. If one were to draw a map of where the lights appear most often, the glowing rings would not align with the familiar lines of longitude and latitude that chart our continents. Instead, they form around the magnetic poles, which drift slowly across the planet over centuries. This means that the best viewing zones shift with time, favoring regions like northern Canada, Scandinavia, and Siberia, not because of geography, but because they sit beneath the paths of magnetic field lines that connect most directly to space. Travelers who chase the aurora must therefore follow magnetism rather than maps, seeking out those invisible corridors where charged particles naturally descend. The pattern underscores how profoundly magnetism shapes our relationship to the cosmos. The world we navigate by surface coordinates is only one version of Earth. Another, unseen, lies above us, defined by fields that curve and flow far beyond the reach of any compass. The best auroras happen around magnetic midnight. Unlike the midnight marked by clocks, magnetic midnight is the moment when a location's magnetic pole is directly aligned between Earth and the Sun, placing the region on the planet's night side of the magnetosphere. At this hour, the long magnetic tail stretching behind Earth is most charged and tense, filled with particles waiting to cascade back toward the poles. When reconnection happens in that tail, streams of electrons surge along field lines toward the upper atmosphere. The result is a sudden boom of color that peaks in intensity just as the rest of the world lies in deepest shadow. The air feels different then, sharper and still, the landscape lit only by stars and the sweeping motion of green and violet fire. Around magnetic midnight, Earth itself seems perfectly tuned to receive the energy of space, and the sky answers with its most luminous display. Equinoxes bring stronger auroras when Earth's tilt aligns just right. Twice a year, in March and September, our planet's axis leans neither toward nor away from the Sun. During these seasons, the solar wind interacts with Earth's magnetic field at just the right angle to open pathways for energy to flow inward. The result is a magnetic configuration that favors reconnection, the process that releases power into near-Earth space. Scientists call this the Russell-McFerran effect, a subtle but reliable rhythm that makes the equinox months famous for vivid auroras. Long nights in the northern hemisphere provide the darkness needed to see them, and travelers who plan their journeys around these dates are often rewarded with breathtaking skies. It is as though the balance of light and dark invites the cosmos to play its brightest song, a moment when the geometry of our orbit conspires with the sun's breath to paint the atmosphere in living color across both poles of the world. Auroras can reach 200,000 degrees in the upper atmosphere. Far above the ground, where air thins into near vacuum, the electrons rushing down magnetic field lines strike atoms with astonishing energy. Each collision transfers heat into a region scientists call the thermosphere, where temperatures soar to hundreds of thousands of degrees Celsius. Yet that heat would not be felt by human skin, for the air is so rarefied that there are too few particles to carry warmth. The energy exists as motion, not comfort, a realm where speed replaces sensation. Instruments aboard satellites record these extremes, mapping invisible temperature waves that accompany every burst of auroral light. This intense heating also expands the atmosphere upward, subtly altering satellite orbits and even changing the drag they experience. The numbers may sound impossible, but they reveal how fiercely alive the upper air becomes during storms, how a thin halo of gas can flare into a furnace when touched by the sun. One bright aurora can release enough energy to power a small city. The dazzling beauty we see as color is only a fraction of the total energy coursing through the system. During a strong event, immense electric currents flow along magnetic field lines into the polar atmosphere, depositing gigawatts of power. Scientists estimate that a large auroral display can equal the energy consumption of a modern metropolis for several minutes. Most of that energy is transformed into heat and light, scattered invisibly across vast regions of air. The scale of these numbers reminds us that the aurora is not a delicate phenomenon, but a planetary engine converting solar wind into terrestrial motion. If humanity could safely harness such currents, they would supply endless power. Instead, we stand below them in wonder, knowing that this brilliance is nature's own electricity, too immense to tame. What we glimpse as graceful color is the visible shimmer of forces that silently drive the planet's magnetosphere. Even faint auroras cover more area than continents. A modest aurora seen from the ground might look like a single band of light stretched across a northern horizon, but from orbit, it reveals itself as part of a sprawling structure that dwarfs the landscapes beneath it. Satellite imagery shows sheets of brightness, hundreds to thousands of kilometers wide, arching over oceans and mountain ranges with ease. The auroral oval encircles the pole like a ring, and even during quiet space weather, the ring spans regions larger than North America. What the eye perceives as local and fragile is, in truth, immense and stable, an atmosphere-wide performance unfolding simultaneously above countless observers. This sense of scale is humbling. The northern lights are not confined to one place or moment. They are a global connection written in motion and energy. Every faint glow glimpsed between clouds is part of a structure so vast that it links nations under one shared sky. Pilots sometimes see auroras glowing outside airplane windows. High-altitude flights over the Arctic and subarctic often bring passengers close to the lower fringes of the aurora, where it hangs like luminous mist above the troposphere. At cruising altitude, the view is transformative. Ribbons of green and violet ripple at eye level, so near that they seem within reach. Pilots flying transpolar routes occasionally adjust cabin lighting to allow travelers to watch, and even those who cannot see it directly notice a faint green sheen across the wings. The experience can feel almost supernatural, a meeting between human technology and a cosmic event older than civilization. For pilots, it is both a spectacle and a navigational reminder that they are flying through space weather as well as air. In the quiet hum of engines, with the world far below, the aurora becomes a silent companion, an ancient phenomenon sharing the sky with the most modern creations of human flight. Satellites have recorded auroras brighter than the full moon. During intense geomagnetic storms, the upper atmosphere can shine with such concentrated energy that the light becomes comparable in brightness to lunar glow. Instruments aboard Earth-observing satellites measure these events in ultraviolet and visible wavelengths, revealing peaks of luminosity far beyond what human vision alone can perceive. From space, the polar regions appear as halos of emerald fire, radiant enough to illuminate cloud tops thousands of kilometers away. These extraordinary displays occur when immense currents surge into the ionosphere, saturating the air with energetic particles. To someone standing beneath them, the brightness can make snow gleam and shadows appear where none should be in the middle of the night. The sky feels charged, as though day and night are blending. For scientists, such moments provide valuable data about the limits of our planet's interaction with the sun, when beauty and power converge in dazzling, measurable brilliance. The same storms that create auroras can endanger astronauts. When solar eruptions send high-energy particles toward Earth, The planet's magnetic field catches most of them and funnels the rest into the poles, creating the aurora. But astronauts in orbit, especially beyond the protection of the magnetosphere, face those same particles directly. During strong events, radiation levels can rise enough to damage cells and electronics alike. Space agencies monitor solar activity constantly, ready to move crews into shielded compartments when a burst approaches. For those aboard the International Space Station, seeing the aurora from above is breathtaking, but it also serves as a reminder of the thinness of their shelter. The glowing bands below mark the very boundary that protects them. Every brilliant arc of color is also a sign of the storm's strength, a visual echo of energies powerful enough to threaten life in space, even as they create wonder for those watching safely from the ground. Earth's aurora is part of a vast magnetic bubble called the magnetosphere. This invisible structure surrounds the planet like an enormous shield, sculpted by the constant flow of solar wind. It deflects most of the sun's charged particles, channeling them around Earth and only allowing a fraction to slip through near the poles. The magnetosphere stretches far beyond the atmosphere, a dynamic region filled with plasma, magnetic waves, and trapped radiation. Within it, storms brew when the solar wind grows turbulent, sending surges of energy through its boundaries. These disturbances spiral inward and ignite the aurora where the magnetic field meets the air. Without this magnetic bubble, Earth would be stripped by the sun's wind, its atmosphere slowly eroded away. The aurora, beautiful as it is merely the visible edge of this vast protective system, a luminous signature of the planet's defense against the raw forces of space that continually try to reach the surface below. Solar wind stretches that bubble into a tail millions of kilometers long. As streams of charged particles blow from the sun, they press against the magnetosphere on Earth's sunlit side and drag it outward on the mid side, forming a long magnetic tail that trails behind the planet like a pall. Comets wake. This tail is where much of the drama begins. Energy accumulates there, twisting magnetic lines until they reconnect and fling particles back toward Earth in brilliant outbursts that light the polar skies. The magnetotae can extend beyond the orbit of the Moon, invisible but alive with motion. Spacecraft passing through it measure sudden jolts of plasma and flashes of magnetic realignment. In a sense, the aurora we see is only the visible end of that cosmic tail, a bright echo of distant turbulence. When the solar wind strengthens, the tail tightens and hums with potential, ready to send another pulse of light sweeping across the polar night. Magnetic reconnection in the tail triggers bursts of light called substorms. Deep within Earth's stretched magnetic tail, tension builds as solar wind drags the field far from equilibrium. Lines of magnetism twist and snap into new configurations, releasing pent-up energy that races back toward the poles. This process, called magnetic reconnection, is invisible in the vacuum of space, yet its effects blaze across the night sky moments later. A quiet aurora suddenly brightens, curtains surge, and light floods the horizon as the storm within the magnetotail breaks. These substorms are the heartbeat of the aurora, brief but intense, each one releasing enough energy to rival a volcanic eruption. Instruments aboard satellites record the sudden acceleration of charged particles, as if the entire magnetosphere had exhaled at once. For those on the ground, the transformation feels almost alive, a whisper becoming a roar of color, the sky awakening as Earth and Sun exchange another electric breath. Substorms make the aurora brighten and dance wildly in seconds. When the stored energy from Earth's magnetic tail finally rushes toward the poles, the calm arcs of the aurora erupt into frantic motion. Curtains that once drifted gently begin to twist and leap, forming ribbons that curl, split, and spiral in every direction. The brightness intensifies until the ground below glows faintly with reflected green light. Within minutes, the display can shift from peaceful to chaotic, as though the atmosphere itself has begun to move with a living pulse. Scientists studying substorms use cameras and magnetometers to trace the timing of these surges, revealing that they unfold in complex waves, not as a single event. The phenomenon lasts only a short while before fading back into calm, but it leaves behind a sense of astonishment that lingers. Each wild dance of color is the visible trace of forces rearranging themselves in the unseen architecture of near-Earth space. Tiny magnetic variations shape every ripple in the sky. To the casual observer, the aurora seems smooth and fluid, yet its motion is governed by minute fluctuations in magnetic strength, measured in fractions of a nanotesla. These tiny tremors ripple through the ionosphere, guiding where electrons descend and how the light spreads across the night. Sensitive instruments detect these subtle wobbles as the aurora shimmers, proving that even the smallest disturbances can sculpt immense beauty. It is magnetism made visible, chaos rendered graceful. The ripples move like wind over water, revealing turbulence in the plasma above, where particles drift along invisible highways of force. In this way, the aurora becomes a living map of magnetic change, painting the air with data that scientists can read like handwriting. The sight of those delicate folds reminds us that grandeur often arises from precision, that what looks like art is actually the finest structure of physical law written in motion. Jupiter's auroras are thousands of times more powerful than Earth's. The largest planet in the solar system commands a magnetic field so immense it would fill a region of space wider than the Sun itself. When charged particles rain into its poles, they collide with Jupiter's upper atmosphere with astonishing energy, creating auroras that blaze continuously, visible even in ultraviolet light. Unlike Earth's fleeting displays, Jupiter's never sleep. They burn day and night, fueled not only by solar wind, but by the planet's own rotation, which whips its magnetic field into perpetual motion. Spacecraft such as Juno have captured images of colossal ovals circling the poles, glowing like electric crowns. These luminous storms reveal how differently magnetism can behave on worlds of varying scale. What we see as a brief nightly wonder on Earth becomes on Jupiter a constant, roaring blaze, a cosmic torch that reminds us how vast and varied the universe's magnetic life truly is. Jupiter's moon Io feeds its aurora with volcanic material. Io, the most volcanic body in the solar system, constantly spews sulfur and oxygen into space, creating a vast cloud of charged gas that orbits alongside the moon. Jupiter's immense magnetic field captures this material and drags it along, accelerating it until it collides with the planet's upper atmosphere. Where those particles strike, they form glowing footprints, bright spots embedded within the greater auroral ring. Each time Io moves through Jupiter's field, it leaves a shimmering trail of energy behind, a visible connection between moon and planet. The process is so powerful that electric currents flow along magnetic lines between the two worlds, generating millions of amperes of electricity. To observe Io's role in Jupiter's aurora is to see an entire moon acting like a generator, feeding its parent with both energy and beauty. Their partnership is a cosmic duet, a magnetic tether stretching across hundreds of thousands of kilometers in space. Saturn's auroras glow deep blue and pulse with radio waves. Saturn's magnetic field, though weaker than Jupiter's, is perfectly aligned with its rotation, creating auroras that shimmer with symmetry and elegance. When solar wind strikes its poles, waves of blue light ripple through its atmosphere, a color caused by hydrogen atoms releasing energy. spacecraft instruments detect simultaneous bursts of radio emissions that pulse in rhythm with the planet's spin, as though Saturn were singing through its own aurora. These invisible sounds allow scientists to measure the length of Saturn's day and track changes in its magnetosphere over time. In visible light, the displays appear delicate, like thin circles of flame etched into the planet's night side. Yet their source is immense, driven by solar storms and internal dynamics that ripple through the gas giant's vast magnetic shell. Saturn's auroras reveal a world both disciplined and dynamic, where light and radio together compose a symphony only space can hear. Uranus and Neptune twist their auroras into strange, tilted shapes. Unlike most planets, Uranus and Neptune have magnetic fields that do not align neatly with their rotation axes. Instead, they are wildly tilted and offset, producing auroras that do not circle the poles but wander across the atmosphere in unpredictable arcs. When the solar wind reaches them, the interaction changes constantly as their unusual fields spin, creating complex and shifting displays. Observations from the Voyager spacecraft and powerful telescopes show that their auroras appear in different places with every rotation, defying the tidy symmetry seen on Earth and Saturn. These erratic lights reveal how planetary magnetism can be both structured and chaotic, sculpted by internal motions we still barely understand. The tilted fields act like cosmic kaleidoscopes, twisting the charged particles into new paths with each turn. Their wandering glows remind us that beauty in the universe often comes from imperfection, from worlds that refuse to behave by simple rules. Even brown dwarfs can have their own auroras. Brown dwarfs exist in the mysterious space between stars and planets, too small to ignite full nuclear fusion, yet too massive to be ordinary worlds. Astronomers once thought them cold and dark, but radio telescopes have detected bursts of emission identical to those produced by auroral processes. These faint objects generate magnetic fields hundreds of times stronger than Earth's, and their atmospheres glow faintly where those fields interact with surrounding plasma. Some of the radio signatures pulse with regularity, suggesting rotating auroral ovals like those of giant planets. In some cases, the energy released rivals that of an entire stellar flare, a beacon shining from an object barely visible in optical light. The discovery of auroras on brown dwarfs has blurred the boundary between stars and planets, showing that magnetism is universal. Even failed stars carry the spark of the same cosmic dance that lights our polar skies at night. Auroras reveal how magnetic fields connect planets to stars. Every beam of auroral light is the endpoint of an electric circuit, linking a world to its cosmic environment. Charged particles flow along these lines of connection, carrying information about the magnetic conditions between planet and star. By studying how auroras behave, scientists can infer the strength, shape, and orientation of these fields across vast distances. The principle applies beyond our solar system, helping astronomers imagine what might happen on exoplanets orbiting active suns. In this way, auroras become more than beauty. They are diagnostic tools, messages encoded in color and rhythm. The shimmering skies of Earth, Jupiter, and Saturn are each chapters in a much larger story about how energy flows through space. Every glowing curtain and pulsing ring is proof that magnetism binds the universe together, that every planet is, in some way, still listening and responding to the song of its parent star. Every aurora maps the invisible forces shaping our world. The displays we see from mountain ridges and icy lakesides are not random acts of light, but precise visualizations of how Earth's magnetic and electric environments evolve in real time. Satellites orbiting above record the same movements as shifting lines of data, yet from below, we witness them as art in motion. Each filament of brightness corresponds to a current, each pulse to an exchange of energy between Earth and the Sun. The aurora, then, is both phenomenon and language, translating the unseen dynamics of our planet into a form we can perceive. It shows where the magnetosphere bends and breathes, how the solar wind molds our protective field, and how fragile and resilient that field truly is. To stand beneath the aurora is to see the shape of the unseen, the living geometry of a planet in constant dialogue with the cosmos that gave it life. Proton auroras glow faintly red and diffuse. Most auroras are made by electrons rushing down magnetic field lines, but sometimes protons take their place. These heavier particles arrive more slowly and interact differently with the upper atmosphere. When they collide with oxygen and nitrogen atoms, the result is not the sharp green or purple curtains most people imagine, but a soft, hazy red glow that spreads gently across the sky. It lacks the structure and movement of typical auroras, appearing instead as a quiet blush over the horizon. Scientists study proton auroras with instruments sensitive to ultraviolet light because they are often invisible to the human eye. The glow forms high above Earth, where air is too thin for collisions to happen quickly, allowing the red light to linger. Though subtle, these rare displays remind us that the aurora has many forms, each created by a different kind of traveler from the sun. Black auroras appear as dark voids within the light. On rare nights, the aurora does something unexpected. Within a bright curtain of color, dark lanes open up and move across the sky, shapes that seem to erase light rather than emit it. These ghostly figures are called black auroras. They are not shadows, but regions where electric fields prevent charged particles from reaching the atmosphere. The absence of collisions leaves narrow paths of darkness winding through the glowing air. To the human eye, they look like rivers of night, flowing through the light itself, twisting and changing shape in silence. Scientists think these patterns reveal how energy is redistributed during the final stages of a geomagnetic storm. They mark boundaries where the magnetosphere begins to relax after turmoil. Watching a black aurora can be unsettling, as if the sky is briefly turning inside out, showing that even within light, darkness can move with its own deliberate grace. Steve is a mysterious purple streak, unlike normal auroras. In recent years, photographers across Canada and northern Europe began capturing a thin violet band stretching from east to west, far south of the usual auroral zones. At first, scientists assumed it was part of a normal display, but the data told a different story. The light, now nicknamed Steve, short for strong thermal emission velocity enhancement, comes from a narrow flow of hot plasma racing through the upper atmosphere. It glows because the air itself is heated to extreme temperatures, not because particles are colliding in the usual way. Steve color is distinct, with a soft magenta or mauve tone that stands apart from green auroras. It can span continents, forming a perfect stripe that lasts for nearly an hour. The discovery proved that Earth's magnetic system still hides surprises, and that new forms of natural light can appear even in skies we thought we already understood. Steve forms from plasma flows far south of auroral zones. Unlike typical auroras that cluster near the poles, Steve appears much farther south, in skies that rarely see such light. The flow that creates it is narrow, fast, and incredibly hot. Plasma streams along magnetic field lines, generating friction where it meets cooler air. The molecules there release light as they are warmed, producing the distinctive purple hue. Satellites flying overhead have recorded temperatures exceeding 3,000 degrees Celsius in this narrow band. Steve is not limited to high latitudes and can appear above cities that normally lie outside the auroral oval. It is one of the few phenomena discovered through cooperation between citizens and scientists, sparked by patient night photographers comparing their images. Its appearance challenges old assumptions about where space weather can reach and reminds us that the Earth's magnetic boundaries are not fixed lines, but breathing edges shaped by the sun's restless energy. Green picket fences often shimmer beneath Steve. Beneath the main purple band of Steve, observers sometimes see rows of narrow green columns flickering quickly, as though a line of tiny torches were burning beneath the larger glow. This pattern is called the green picket fence. It forms when waves of energy from the upper plasma flow interact with oxygen atoms at lower altitudes. Each vertical bar lights up as electrons rain down, then fades as the next one brightens, creating a fast rhythm of movement across the sky. The effect is mesmerizing, a pulsing layer of emerald fire under a violet arc. High-speed cameras show that the pattern shifts and ripples in response to invisible forces from above, linking the two layers in a complex dance. The green picket fence is still being studied, but it offers a rare glimpse into how multiple atmospheric layers can respond together to the electric music of a geomagnetic storm. Auroras can create radio signals detected far out in space. The same charged particles that light up the night sky also produce bursts of radio energy that travel through the magnetosphere. Spacecraft far from Earth have picked up these emissions, translating them into sound waves that can be played back as eerie whistles and chirps. The signals are created as electrons spiral along magnetic field lines, generating electromagnetic waves that escape into space. These radio voices reveal how powerful the auroral process truly is, carrying information across millions of kilometers. Scientists use them to study how energy moves between the Earth and the Sun, since the patterns of pitch and rhythm encode details about the magnetic environment. Some spacecraft detect these signals long before the aurora becomes visible from the ground, offering early warning of storms to come. It is as if the sky sings before it glows, its invisible notes traveling through the silent vacuum of space. Those signals help map Earth's magnetic field. By listening to the aurora's radio emissions, scientists can trace the shape of our magnetic field in motion. When spacecraft detect the timing and strength of these bursts from different positions, the data reveals where magnetic lines bend or reconnect. Ground stations add their own observations, and together they form a moving picture of Earth's invisible architecture. The process turns the planet into a natural observatory, using its own music to describe its design. These measurements improve space weather forecasting and help engineers protect satellites and power systems from disruption. Each signal becomes a data point in the living map of magnetism that surrounds us. Even though the sound is beyond our hearing, it carries the same story as the aurora itself, showing that beauty and information can emerge from the same physical dance. The light we see and the signal we cannot are parts of one continuous song. Pulsating auroras blink in hypnotic rhythm. Some auroras do not drift smoothly but flash and fade in a steady beat. These pulsating patches appear after substorms, when waves in the magnetosphere regulate the flow of incoming electrons. The sky becomes a slow strobe, with patches of green or white light blinking in patterns that seem almost alive. The rhythm can be steady or uneven, lasting minutes or hours, with pulses separated by seconds or fractions of a second. Scientists studying them have found that electromagnetic waves traveling through the magnetosphere guide the timing of these flickers, controlling when and where electrons enter the atmosphere. To those watching from below, the effect is both calming and surreal, as if the heavens are breathing in and out. In the silence of night, the steady pulse of light feels like the heartbeat of the planet itself, echoing through the air in the language of color and motion. Omega auroras form giant loops floating like glowing waves. Among the rarest shapes in the sky are the great arches that resemble the Greek letter omega. They appear when electric currents bend magnetic field lines into looping forms that reconnect beneath themselves. The result is a glowing bridge of light that floats across the horizon like a celestial wave. These loops can span hundreds of kilometers and drift slowly as the magnetic tension shifts. To scientists, they mark boundaries where plasma flows collide and reorganize, creating a temporary structure of perfect symmetry. To anyone watching from the ground, they look almost solid, like gateways or crowns made of light. The loops rise, stretch, and dissolve as quickly as they form, leaving behind a feeling of serene strangeness. Omega auroras show how order can emerge from turbulence, how even the most chaotic forces in space can find balance long enough to sketch beauty upon the dark canvas of night. The aurora can trigger atmospheric gravity waves across continents. When a geomagnetic storm releases energy into the upper atmosphere, it does more than paint the sky. The sudden heating and motion create ripples that spread downward through the layers of air below. These ripples, called atmospheric gravity waves, move across entire continents, influencing winds and temperature patterns thousands of kilometers away from the poles. Scientists detect them with satellites and weather balloons, tracing faint oscillations in pressure and density. Though invisible to the human eye, their presence links space weather to the climate system below. The aurora becomes not just a light show, but a driver of subtle changes in the air that we breathe. Every burst of color sends a tremor through the planet's atmosphere, a quiet reminder that Earth and space are deeply connected. Even as the light fades, its echoes continue to ripple through the unseen fabric of the world. Auroral energy heaps the upper atmosphere until it swells outward. When solar particles stream into the poles, they strike atoms in the thin upper air and pour vast amounts of energy into the atmosphere. The collisions create heat in regions that are usually close to the edge of space, causing those layers to expand and rise. This swelling is invisible from the ground, but measurable from orbit, where satellites detect the atmosphere reaching higher than usual. The change can last for days, altering how gases mix and how radio waves travel through the ionosphere. Scientists study these fluctuations to understand how space weather can reshape the very boundary of our world. The process links the glow of the aurora with the physics of the air itself, turning beauty into motion. Each time the lights blaze across the night sky, they also make the atmosphere breathe a little deeper, lifting the edge of Earth closer to the cold emptiness of space. Satellites in low orbit can experience extra drag during storms. When the upper atmosphere expands from auroral heating, its density increases even in regions far above the clouds. Satellites that normally circle Earth through near-vacuum conditions suddenly find themselves encountering more resistance than expected. This drag slows them down, changing their orbit little by little. Over time, if the storm continues, they can lose altitude and begin to fall toward denser layers below. Space agencies must monitor these effects carefully, using thrusters to correct the satellite's path and prevent damage. During particularly strong geomagnetic storms, entire groups of small satellites have been lost because the atmosphere expanded too quickly for operators to respond. The invisible force that paints the poles with color can therefore reach far beyond its light, tugging gently on machines that circle the planet. It is a humbling reminder that even human technology must move in rhythm with the restless breathing of Earth and Sun. Auroral currents travel along magnetic field lines like cosmic wires. The glowing curtains of the aurora are only the visible edge of an immense electrical circuit. Streams of charged particles flow along magnetic field lines that connect space to Earth's poles. These currents move with steady precision, carrying energy from the magnetosphere into the upper atmosphere. When they strike atoms in the air, the collisions release light and heat, completing the circuit. Instruments aboard satellites record these flows as strong variations in magnetic strength, while ground sensors detect the same energy passing beneath the surface. The system functions like a natural power grid on a planetary scale, running silently across the sky. Its electricity would be overwhelming to any human device, yet it operates with elegance and balance. These cosmic wires link the Sun to the Earth in a vast loop of motion, turning invisible magnetism into one of the most beautiful sights ever witnessed from the ground. Those currents can induce electricity in pipelines and railways. When geomagnetic storms send electric currents through the atmosphere, they also generate slower secondary currents across the surface of the planet. Long metal structures such as pipelines and railway tracks act like antennas, picking up this energy as it moves through the ground. Engineers have measured voltage differences strong enough to interfere with equipment or accelerate the corrosion of buried pipes. In extreme cases, the flow can cause sensors to give false readings or overload circuits connected to the grid. These effects are most common during powerful auroral events, when the currents in the sky above are strongest. Modern infrastructure is designed with grounding systems that reduce the risk, but the phenomenon remains an active area of study. It shows that the aurora is not limited to the heavens. Its power can reach into the soil beneath our feet, weaving through the skeleton of human industry with quiet precision. Telegraph operators once saw sparks jump from their lines. In the early days of long-distance communication, before the invention of modern electronics, telegraph networks stretched for thousands of kilometers across open land. During powerful auroral storms, operators began reporting strange and sometimes dangerous behavior in their equipment. Metal wires buzzed, needles moved without any signal being sent, and sparks leapt between contacts even when batteries were disconnected. The natural currents induced by geomagnetic disturbances flowed directly into the telegraph systems, turning them into unintended receivers of the Earth's magnetic heartbeat. Some operators used the energy to send short messages after disconnecting their power supplies, amazed that the sky itself was carrying their words. These stories became famous examples of the aurora's strength long before space science existed. The lights dancing above were not just a spectacle, but a physical force strong enough to speak through copper, a living reminder that nature itself could power communication across the world. In 1859, a massive storm shocked telegraph offices. The Great Geomagnetic Storm of 1859, known today as the Carrington event, remains the most powerful solar storm ever recorded. When the blast from the sun reached Earth, auroras appeared around the world, glowing as far south as the Caribbean. Telegraph operators reported violent surges of electricity racing through their lines. Some systems caught fire, while others continued to send messages even after being disconnected from their batteries. The storm disrupted communication networks for days and left observers astonished at the scale of the phenomenon. Scientists later realized that an immense ejection of plasma from the sun had struck Earth's magnetosphere, flooding it with energy. The event revealed both the beauty and the danger of space weather, showing that the forces behind the aurora could reach deep into human civilization. It stands as a warning of what might happen if such a storm were to occur today. A similar storm today could disable satellites and power grids. Modern society depends on technology that is far more sensitive to electromagnetic disruption than the telegraph systems of the past. If a storm like the Carrington event struck today, satellites could be damaged, communication systems might fail, and electrical grids could collapse. High-voltage transformers are especially vulnerable to the slow currents that geomagnetic storms create in power lines. Entire regions could experience prolonged blackouts while equipment is repaired or replaced. Airlines would need to reroute flights away from the poles to avoid navigation problems, and radio networks could fall silent for hours. Scientists around the world now monitor solar activity constantly, hoping to predict such storms before they reach Earth. Early warning systems give engineers time to disconnect sensitive circuits or adjust satellite positions. Even so, the prospect remains daunting. The same magnetic power that lights the sky with beauty could also remind us of our planet's delicate dependence on balance. Auroras are most frequent where Earth's magnetic field is strongest. The magnetic field acts as a funnel, guiding solar particles toward the poles. Regions where the field lines converge experience the highest concentration of energy, which is why auroras are most often seen in high-latitude countries. These zones, known as the auroral ovals, shift slightly as the magnetic poles wander over time, but they remain close to the northern and southern extremes of the globe. Within these regions, the lights can appear many times each week during active seasons, creating a near-constant show for those who live there. Scientists studying the phenomenon note that variations in magnetic intensity directly influence the height and brightness of the aurora. Stronger fields produce sharper, more defined curtains of light, while weaker fields spread the glow more thinly across the horizon. The frequency of auroras is therefore both a reflection of Earth's magnetism and a measure of how deeply we are connected to the Sun. In Alaska and Norway, locals see them many times each winter. In the far north, the aurora is not a rare visitor, but a familiar companion. Communities in Alaska, Norway, and parts of Canada often experience dozens of displays each year, lighting the long winter nights with shimmering color. Residents grow up watching the sky flicker and move, learning to sense when the lights might return. Travelers arrive from around the world, hoping to witness what locals consider an almost ordinary wonder. For scientists, these regions provide natural laboratories where the aurora can be studied in detail using cameras, magnetometers, and satellites overhead. For those who live there, the phenomenon becomes part of the rhythm of life, marking seasons and memories. The lights appear differently each time, sometimes as quiet veils, sometimes as brilliant storms that cover the whole sky. In these frozen lands, the aurora is woven into culture, science, and daily experience alike, a bridge between tradition and discovery. The southern lights are brighter, but often hidden by storms. In Antarctica, the aurora australis shines with colors as vivid as its northern twin. The southern magnetic field is slightly stronger and more compact, which means that the lights there can burn with greater intensity. From the icy plateaus, the sky can turn entirely green, then red, then violet as particles strike the atmosphere. Yet few people ever see it. The continent's fierce weather often hides the display behind layers of cloud and snow. Researchers stationed at Antarctic bases sometimes glimpse it during rare, clear nights, describing the sight as almost overwhelming. Satellites record its beauty from above, even when it cannot be seen from the ground, proving that the southern lights are no less grand than those of the north. The aurora australis remains one of Earth's least witnessed wonders, glowing unseen over the world's most remote horizon, a reminder that beauty does not depend on being observed to exist. Daytime, auroras glow in ultraviolet light, invisible to us. When the sun is high and the world is bright, the atmosphere can still be alive with energy near the poles. Charged particles pour along magnetic pathways and collide with rarefied gases exactly as they do at night, but most of the glow arrives in ultraviolet wavelengths that human eyes cannot perceive. The blue sky simply masks the subtle, visible traces that might otherwise appear. Specialized instruments show that these daytime displays can be broad and dynamic, with structures that ripple and reform while the ground below looks ordinary. The phenomenon proves that auroral activity does not depend on darkness. only on the flow of energy into the upper air. Even at noon, the planet wears a hidden crown. What looks like an empty sky over snow and sea ice can, in truth, be a stage where light performs beyond the limits of our own vision. Satellites capture those hidden auroras from space. Orbiting observatories carry detectors that sense ultraviolet wavelengths and map the glow circling the poles in daylight. From above the atmosphere, their view is unobstructed by air scattering or weather. The instruments trace rings and arcs that shift with solar wind conditions, revealing where energy is entering the atmosphere in real time. Scientists combine these images with measurements of particle flux and magnetic orientation to understand how storms evolve through a day. The records show that daytime auroras can be as structured as their nighttime counterparts, complete with arcs, patches, and sudden brightenings. This vantage turns invisibility into data, giving a continuous picture of activity that ground observers cannot obtain. In a single orbit, a satellite can watch the auroral oval breathe, then pass the information to forecasters who monitor space weather for aviation and communications. The lights are always writing, and satellites provide the pen. The first aurora photographs were taken in the 19th century. Long before digital sensors, patient photographers braved winter nights with fragile glass plates and slow emulsions, aiming to trap the faint glow on film. Exposure time stretched into many minutes, and every gust of wind threatened to blur the scene. Yet those early images revealed arcs and veils that matched careful drawings in scientific journals, proving that the camera could record what the eye only glimpsed. The effort required meticulous planning, from tracking the stars to compensate for Earth's rotation, to shielding equipment from frost. Each successful plate became both art and evidence, a preserved moment from a sky that never holds still. These photographs helped establish auroral research as a precise discipline, allowing measurements of shape, height, and motion that could be compared across years. In the dim chemistry of those plates, a new way of knowing the polar night was born, turning wonder into a lasting record. Modern cameras reveal colors invisible to the human eye. Digital sensors can integrate light over long intervals and respond to wavelengths where human vision is weak. In darkness, our eyes favor shades of green, while cameras gather faint blues, violets, and subtle reds that would otherwise be lost. Photographers use fast lenses and careful exposure to coax delicate hues from the night, and the resulting images show layered structures that hint at altitude and composition. What looks to a person like a soft green arc often hides a thread of purple at the edge or a thin red crown above, recorded by the sensor as a quiet secret. These images are not exaggerations. They are translations, faithful to wavelengths our biology ignores. When time-lapse sequences compress minutes into moments, motion itself becomes clearer, revealing patterns that help scientists interpret physical processes. The camera becomes a bridge between perception and reality, expanding the palette of the polar sky. Aurora colors shift depending on how fast atoms are excited. When energetic particles strike oxygen and nitrogen at different speeds, they jolt electrons to specific levels inside those atoms and molecules. The route back down determines the shade that appears. Higher energy interactions can open transitions that glow red in thin upper air, while moderate energies favor the familiar green at lower heights. Rapid collisions in denser layers produce the purples and blues of molecular nitrogen, especially along fast-moving edges. The tempo of excitation sets the balance of colors seen from the ground, and that tempo changes as the storm strengthens or relaxes. Even within a single arc, edges and cores may differ because the rate of impact is not uniform. By reading the colors, trained observers infer altitude, density, and the vigor of the incoming flow. The sky becomes a spectrum in motion. with each hue a clue to speed, depth, and the momentary mood of space. Auroras can appear as faint arcs or vast draping curtains. On a quiet night, a single dim band may rest along the horizon, steady and pale, like a shoreline of light. Give the system more energy and the band unfolds, falling into overlapping sheets that reach high above the observer, with folds and pleats that sway as if stirred by a tide. The difference in form reflects how energy enters the ionosphere. Gentle flows favor thin arcs aligned east to west, while stronger surges inflate the structures into multi-layered draperies that can cover much of the sky. From within those curtains, stars blink and vanish as edges pass by, and distant mountains take on an otherworldly glow. Pilots and astronauts see the same shapes from different angles, recognizing the geometry as a projection of field lines onto air. Shape follows physics. The arc is a boundary. The curtain is a flood. Both are chapters of the same story. Some auroras form crowns that radiate overhead. Stand near the center of the oval and look straight up during a strong display, and the lines of light can seem to converge into a starburst. Rays shoot outward in every direction, giving the impression that the sky has opened into a glowing flower. This crown appears when the observer stands beneath a region where field lines point almost directly downward, so the long vertical rays are foreshortened into a central hub. The effect is intensely immersive, as if the aurora is descending rather than drifting sideways. Photographs from such moments preserve a radial pattern with surprising symmetry, yet the experience is even richer in person, because the rays flicker and advance. The crown marks a crossing of vantage and structure, a point where perspective reveals the three-dimensional nature of the display. For a few minutes, the dome of night seems to rest on a living throne of light. The corona effect happens when magnetic lines point toward you. The crown that blooms overhead is not a change in the aurora itself, but a change in how it is seen. When long rays align with the line of sight, perspective compresses them into a central point from which all motion appears to radiate. Move a short distance across the snow, and the geometry dissolves back into parallel curtains. The effect depends on standing within a narrow zone where the local magnetic direction matches the gaze. Observers sometimes search for it by walking under an active arc until the pattern snaps into place. A sudden shift that feels like stepping through an invisible doorway. The corona demonstrates how structure lives in three dimensions, while our view is a projection. It is proof that the sky contains depth and direction beyond what any single position reveals, and that the most dramatic formations can arise from alignment as much as from power. Auroras begin as small glowing patches in the sky. Before an arc stretches across a horizon, the first signs often appear as quiet pools of light. These patches brighten and fade in place, as if testing the air for permission to grow. Instruments detect subtle changes in local currents at the same time, showing that energy is building along connected field lines. As the patches multiply, they link into segments, then into a loose arc that wavers and finds a stable path. The early stage is easy to miss because it lacks motion and drama, yet it holds the seed of the storm to come. Observers who learn to watch for these hints often know a grander display is near. The transformation from patch to ribbon is a transition from scattered energy to organized flow, a moment when the atmosphere begins to behave like a single instrument. The first faint glow is not a decoration. It is a promise. Scientists call this build-up the growth phase. In this stage, the magnetotal stores energy as the solar wind stresses the field far behind Earth. Lines of magnetism stretch and thin, while the ionosphere quietly prepares to conduct stronger currents. On the ground, instruments record rising magnetic tension, and all sky cameras see arcs sharpen and extend. The growth phase can persist from minutes to more than an hour, a patient gathering before release. It ends when reconnection snaps the distant field and sends accelerated particles racing toward the poles. What follows is the quick bloom that most people remember, but without the careful preparation, there would be no storm to see. Naming this interval gave researchers a way to compare nights and identify patterns that repeat across seasons and solar cycles. The term captures a truth about the spectacle. The beauty that erupts across the sky is planted quietly, then nurtured by time and unseen force. The expansion phase erupts into light across the sky. After a long period of gathering tension, the magnetosphere releases its stored energy in a sudden cascade. Magnetic lines reconnect far behind Earth, flinging charged particles toward the poles at tremendous speed. In moments, quiet arcs burst into motion. Curtains of green and violet unfold from horizon to zenith, twisting and surging like waves in an unseen ocean. The air crackles with invisible power as electrons strike oxygen and nitrogen, turning the upper atmosphere into a living canvas. This expansion phase is the climax of the substorm, when everything that was held in silence becomes motion and color. To observers, it feels as though the entire sky has awakened, alive with movement too grand to comprehend. Satellites detect rapid changes in current, and magnetic readings on the ground spike sharply. It is the storm's heartbeat made visible, the Earth exhaling the energy it has gathered from the sun. The recovery phase leaves a fading afterglow in space. When the magnetosphere finally releases its built-up energy, the system begins to settle. Electric currents weaken, and the bright curtains of the aurora slowly dissolve into pale arches. The charged particles that once poured toward Earth diminish, leaving behind faint traces of warmth in the upper atmosphere. Scientists call this interval the recovery phase. Instruments show the magnetic field gradually returning to its normal shape, like a stretched cord returning to rest. From the ground, the change feels peaceful. The sky grows still again, its lights dimming to the faintest whisper of green before vanishing completely. Yet remnants of the storm linger in space for hours. Waves of plasma ripple outward through the magnetosphere, carrying echoes of the event deep into the solar wind. What remains is memory, both in data and in the hearts of those who watched. A soft reminder that even energy eventually comes home to rest. Auroras can change the chemistry of Earth's upper atmosphere. Each time charged particles strike the air, they break apart molecules and create new compounds. This reaction happens far above where weather forms, in a thin layer that still influences the planet below. The collisions produce reactive gases such as nitric oxide and hydrogen oxide, which can drift downward through the atmosphere over time. These compounds play roles in ozone chemistry and the transfer of heat. During strong geomagnetic storms, their concentrations rise enough to alter the delicate balance of radiation that the Earth absorbs and emits. Scientists monitor these changes with satellites that track infrared emissions and chemical fingerprints. The aurora, though beautiful and fleeting, is therefore also a participant in the planet's long-term atmospheric cycle. Every glow marks not just an exchange of energy, but a chemical transformation, a quiet blending of space and air that links distant solar storms to the living world below. Nitric oxide formed during storms can affect ozone levels. In the thin air above the poles, auroral energy breaks oxygen and nitrogen apart, allowing them to recombine into nitric oxide. This gas drifts downward over days or weeks, eventually reaching the stratosphere where ozone resides. There, it reacts with ozone molecules, converting some of them back into ordinary oxygen. The effect is temporary but measurable, especially during periods of intense solar activity. Satellite instruments have traced these patterns, showing how bursts of light at the poles can influence the chemistry of air thousands of kilometers away. While the changes are small compared to human impacts on the atmosphere, they reveal a direct link between space weather and the balance of radiation that governs climate. Nitric oxide acts as a messenger from the upper reaches of the sky, carrying the signature of geomagnetic storms down into the layers where sunlight and life interact. Scientists study auroras to understand how the sun affects climate. By measuring how auroral energy moves through the atmosphere, researchers can trace how solar activity influences temperature, circulation, and chemical composition. The sun's output is not constant. It pulses with cycles of magnetic storms that inject energy into Earth's upper layers, subtly changing how heat flows across the globe. Though the effects are small compared to greenhouse gases or ocean currents, they are important for understanding the planet as a complete system. Instruments aboard satellites record how much ultraviolet light and charged plasma arrive during each solar cycle, while ground-based sensors monitor the response of the ionosphere. Together, these data help scientists build climate models that include the influence of space weather. The study of auroras thus reaches far beyond the beauty of the night sky. It provides insight into how the sun and Earth share energy, a relationship that shapes both our environment and our future. The lights help map currents between the magnetosphere and ionosphere. Every flash and ripple in the aurora corresponds to a current flowing between space and the upper atmosphere. Scientists use ground-based cameras and magnetic detectors to track where these flows enter and exit, mapping the invisible highways of electricity that surround the planet. By combining these observations with satellite data, they can see how power moves from the solar wind into Earth's magnetic field, then down to the ionosphere. The patterns change constantly, tracing paths that expand, twist, and contract with each new burst of energy. Understanding this circuit is essential for predicting how space weather affects satellites, power systems, and communication networks. The aurora, in this sense, acts as a visual indicator of current flow. Its beauty is the surface of a vast and orderly machine, one that runs without sound but reveals its structure through every flicker of color above the frozen poles. Auroras are natural laboratories for plasma physics. The same principles that govern the aurora also shape much of the visible universe. In the upper atmosphere, charged particles and magnetic fields interact in ways that can be studied in real time. Scientists use these events to test theories about how energy moves through plasma, the fourth state of matter that makes up most of the cosmos. By comparing satellite readings of particle motion with ground-based observations of light, they can model magnetic reconnection, turbulence, and wave interactions that occur in far more distant environments. The aurora is both accessible and extreme, offering an atom experiment that repeats night after night. Every event provides data on how plasma behaves when confined by magnetic fields, knowledge that helps refine models of stars, galaxies, and even fusion reactors. In this way, the soft glow above the poles becomes a bridge between the mysteries of Earth and the physics of the stars. The same processes occur near black holes and distant stars. The universe is filled with magnetic fields and plasma, and the mechanisms that shape the aurora appear in far grander settings. Around black holes, jets of charged matter twist along magnetic lines, releasing bursts of light that can span entire galaxies. In the atmospheres of stars, similar reconnection events produce flares and radiation storms. Even the spiral arms of galaxies follow magnetic pathways that guide energy through space. By studying the aurora, scientists can observe these processes in a nearby and manageable form. It serves as a miniature version of cosmic phenomena that are otherwise beyond reach. The equations describing particle acceleration and magnetic tension are the same whether they unfold over kilometers or light years. The shimmering bands above the Arctic night are therefore not isolated curiosities, but echoes of the grand machinery of the universe, where magnetism, matter, and motion weave light from darkness everywhere. Every aurora tells a story of the sun and earth entwined. Each burst of light begins with an eruption on the sun, a surge of plasma that crosses the vast gulf of space and finds the magnetic shield of our planet waiting. The dance that follows is a dialogue between two worlds, one giving energy, the other responding in grace. The patterns of the aurora record the conditions of that meeting, the strength of the solar wind, the tilt of Earth's field, the density of the air above the poles. To watch an aurora is to witness a conversation written in light. Scientists read it as data, but anyone can feel its meaning as connection. It is the visible sign of belonging within a greater system, the living thread that binds our fragile world to its star. Every shimmer and pulse carries a message across 90 million miles, saying that we are not separate, but part of one shared rhythm of creation. Some cultures saw the lights as spirits in the sky. Long before science offered explanations, the people who lived under the aurora gave it meaning in their own languages. In northern Europe and across the Arctic, stories spoke of spirits dancing above the snow, of ancestors lighting torches to guide hunters home, or of animals whose breath glowed against the stars. Some tales described the lights as bridges between worlds, places where souls could cross from the land of the living to the realm beyond. The movement of the aurora mirrored the motion of human life, sometimes calm, sometimes wild. Even today, those stories remain part of the cultural memory of the North. They remind us that wonder and respect were humanity's first responses to mystery. While science has uncovered the physics behind the glow, the older understanding still carries truth. The sky is alive, and in its light, we see reflections of ourselves. Others believed they were messages from ancestors. Across the polar world, the lights were seen as signs from those who came before. Inuit traditions speak of souls playing in the sky, waving to the living through arcs of color. In parts of northern Scandinavia, people believed the aurora carried the voices of the dead, whispering messages that only the heart could understand. Some communities treated the lights with reverence and silence, fearing that whistling or pointing could disturb the spirits and bring misfortune. The aurora's beauty was both comforting and solemn, a reminder that the boundary between worlds was thin beneath its glow. Even today, in remote Arctic towns, elders still tell stories that weave respect and memory together. The science of solar winds and magnetism explains the cause, but not the feeling. That belongs to something older, a sense that the sky remembers us, and that every flicker might be a greeting from beyond time. The aurora has inspired art, music, and legend across the world. Painters have chased its shifting colors, poets have written of its silence, and composers have tried to turn its movement into sound. The aurora's presence awakens the imagination because it refuses to stay still or to be fully captured. In ancient folklore, it became a symbol of divine light or celestial fire. In modern art, it stands for wonder and transformation, for the meeting of chaos and calm. Sculptors carve its shapes into glass and metal, choreographers mirror its flowing rhythm in motion, and musicians evoke its pulse in quiet harmonies. Each generation finds new language for the same mystery. Even in places where the aurora never appears, it lives in stories and symbols, a reminder that beauty can cross every border. The lights invite both artists and scientists to do the same thing, to look upward, to listen closely, and to translate awe into expression. Explorers once used the lights to find their latitude. Before reliable compasses and precise maps, navigators in the far north relied on the heavens for orientation. When auroras appeared, They provided subtle hints about location. The height and shape of the glow changed with latitude, often stretching higher in the north and flattening near the magnetic boundary. Experienced travelers could estimate their position by observing how the arcs moved and where they touched the horizon. This practice was especially useful during long polar nights when the sun remained hidden. Early Arctic explorers kept careful journals of auroral behavior, comparing notes with magnetic readings taken during clear skies. Their observations helped define the region where auroras were most common, leading eventually to the concept of the auroral oval. For them, the lights were not only a spectacle but a navigational tool, one that guided human footsteps through the frozen unknown long before satellites mapped the pathways of the sky. Reindeer sometimes react nervously to the aurora's presence. Among herds in the far north, the sudden appearance of shifting light can cause animals to lift their heads and move uneasily. Some stand motionless, ears alert, while others circle or change direction. Scientists who study their behavior suggest that reindeer may sense subtle changes in the electromagnetic environment during strong auroral activity. The same charged particles that paint the sky could influence how animals perceive sound or static. Indigenous herders have long observed these reactions, treating them as quiet warnings that the heavens are active. The animals seem to notice what humans cannot feel, the faint electric breath of the storm. This sensitivity may come from their remarkable vision, which extends into the ultraviolet range, allowing them to see contrasts invisible to us. To the reindeer, the aurora might not be a distant show at all, but a tangible shimmer in the air around them, alive and close. Cameras can see auroras even when eyes cannot. Long before the first stars emerge, sensitive digital sensors can detect faint traces of auroral light invisible to human vision. Photographers in polar regions often set their cameras to capture time-lapse sequences through the night, revealing ghostly arcs that appear hours before any visible display. These subtle emissions occur when only a few energetic particles reach the upper atmosphere, producing light too dim for the robes and cones in our eyes to register. Yet the camera's patient gaze gathers every photon, building a picture of activity that shows the aurora's quiet beginning. Scientists use similar techniques to monitor the sky continuously, tracking fluctuations in brightness that mark shifts in the magnetosphere. What we see as a sudden eruption of light often has a long, hidden prelude that unfolds in silence. Technology extends our perception, uncovering the first whispers of the storm before the sky bursts into song. From space, Earth's aurora looks like a glowing green ring. Astronauts aboard the International Space Station often describe the aurora as a circular crown wrapped around the poles. From their vantage point above the planet, they can look down through the edge of the atmosphere and see the light stretching for thousands of kilometers. It glows brightest where the magnetic field channels particles most directly toward the surface, forming an oval that pulsates with each burst of solar wind. The sight is breathtaking, a luminous band floating against the blackness of space, with the curved limb of Earth glowing softly beneath it. Time-lapse footage from orbit shows the ring expanding and contracting like a living organism, its edges curling and flaring. For those who witness it, the experience transforms understanding. The aurora is not just a display above the world, but a halo that belongs to the planet itself, marking where Earth meets the stream of power from its star. Space probes have recorded our aurora from millions of kilometers away. Far beyond the orbit of the Moon, instruments aboard passing spacecraft have detected radio emissions and ultraviolet glows coming from Earth's magnetic poles. These signals reveal the presence of the aurora even when the planet is seen as a tiny blue dot. From that distance, the lights appear as shimmering rings that pulse in rhythm with solar activity. By measuring their brightness, scientists can gauge how much energy the planet absorbs from the sun. Some probes use these data to compare Earth's magnetosphere with those of other worlds, helping to explain how magnetic fields protect planets from radiation. The fact that our aurora can be observed across such immense distances shows how powerful it is. In the silent vacuum of space, Earth announces itself not only through light reflected from the sun, but through the glow of its own magnetic breath, shining faintly yet unmistakably across the cosmic dark. Aurora physics could one day help develop fusion energy. The same processes that create the aurora also govern the behavior of plasma inside experimental fusion reactors. Both involve charged particles confined by magnetic fields and energized to extreme speeds. By studying how auroral particles move and how magnetic reconnection releases bursts of energy, scientists learn lessons that apply to controlling plasma on Earth. Understanding these dynamics is crucial for creating stable fusion, the process that powers stars. Laboratory experiments and computer models draw directly from auroral data, using the sky as a natural example of high-energy plasma behavior. The aurora is therefore more than a spectacle. It is a teacher. It shows how magnetic lines twist, how energy is stored, and how it can be released safely. The research born from its study may one day allow humanity to replicate the power of the sun itself, bringing light not from the heavens, but from our own hands. Watching the aurora connects us to both sun and earth. Standing beneath the moving light, one can feel the unity of two vast systems working together. The air shivers with energy that began 90 million miles away, carried by winds of charged plasma that found their way home to our magnetic shield. The ground beneath is equally part of the story, conducting faint electric currents that mirror the patterns above. Every flicker is a dialogue between what lies below our feet and what burns in the sky. To watch it is to sense the scale of connection that sustains the world. The aurora transforms abstract physics into visible poetry, a reminder that we live within the influence of a living star. In that moment, the boundary between cosmic and earthly dissolves. What we call the Northern Lights are really the meeting place of two realms, one made of matter, the other of fire, joined in graceful exchange. The aurora reveals that our planet is part of a larger cosmic web. Magnetic fields thread through the galaxy, linking stars and planets in a vast network of energy. The aurora is our small corner of that web, a visible sign of cosmic structure that otherwise hides in the dark. The currents that travel through our atmosphere continue outward, merging with the sun's magnetic flow and then with the fields that shape the interstellar medium. By studying the aurora, scientists can trace how local and galactic systems intertwine. It teaches that space is not empty, but filled with invisible architecture, a fabric of motion that binds everything together. Each ripple in the sky is connected to distant forces, and the glow above the poles is one luminous knot in an immense tapestry. Watching it, we glimpse our place in that pattern and realize that Earth is not isolated, but woven into the living electricity of the universe. Each flicker is an electron from the sun meeting an atom from Earth. Every burst of auroral light begins as a journey across space. The electron is born in a storm on the sun, flung outward on the solar wind. After traveling millions of kilometers, it finds itself caught in Earth's magnetic field and guided toward the poles. There, in the thin air of the upper atmosphere, it strikes an atom of oxygen or nitrogen. The impact transfers energy, and for a brief instant, that atom glows. The light we see is the record of that meeting, the visible signature of cosmic exchange. Each shimmer in the sky is a story of connection, tracing the path from star to planet, from fire to breathe. It is astonishing that a single collision, happening faster than thought, can become beauty spread across the heavens. The aurora teaches that even the smallest particle can illuminate the vast distance between worlds. The brightest auroras occur when solar wind speeds increase dramatically. When the sun releases a burst of plasma, the solar wind rushes outward with fierce momentum. As it slams into Earth's magnetic shield, the impact compresses the field and channels vast amounts of energy into the magnetosphere. The faster the wind, the stronger the magnetic disturbance, and the more intense the resulting light. During these events, the aurora can fill the entire sky, bright enough to cast shadows on the snow. The colors become deeper and more layered, with red and violet rising above green curtains that twist like flame. Instruments on satellites record spikes in particle flow, while power systems on the ground sometimes feel faint surges. To witness such a storm is to see the living connection between the sun and the earth made plain. The strength of that light is not just brightness, but energy crossing the emptiness of space to write color across the dark. During strong storms, the aurora can outshine the Milky Way. In the darkest places on Earth, far from any human light, the Milky Way stretches overhead as a pale band of ancient stars. Yet during the most powerful geomagnetic storms, even that celestial river fades before the auroras glow. The entire sky can pulse with green and crimson light, bright enough to reveal the landscape in ghostly tones. Mountains and ice fields take on shifting hues, and shadows dance as if the world itself were breathing. Records from explorers and sailors tell of nights when the aurora illuminated the decks of ships or lit pages in open books. Cameras today confirm that these storms can make the upper atmosphere shine 100 times brighter than normal. For a few rare hours, the balance of the night reverses, and the light born from our sun eclipses the light of distant galaxies, a reminder that our own star still holds power beyond measure. Some auroras appear as still glows that never seem to move. Not every aurora dances. Sometimes the light rests quietly, forming a smooth arc that holds steady above the horizon. The air shimmers faintly, yet the structure remains calm, as though the energy has reached a point of perfect balance. These silent glows occur when the incoming flow of charged particles is steady rather than turbulent, producing continuous excitation without strong variations. Scientists observe them most often during the tail end of a storm, when the magnetosphere has released most of its tension. The calm light lingers, soft and even, like an exhale after great exertion. For those watching, it feels different from the bright storms of earlier hours. The stillness invites reflection, the sky no longer a spectacle but a companion. These quiet auroras show that beauty can exist not only in motion and power, but in the serenity that follows when nature finally comes to rest. These quiet glows trace the edges of invisible plasma currents. Beneath the calm surface of a faint aurora, vast electric circuits continue to flow. The steady light outlines the pathways where charged particles drift along magnetic field lines, tracing currents that connect the magnetosphere to the ionosphere. These boundaries act like contours in an unseen map, marking where energy moves and where it fades. Scientists use them to study how the magnetosphere organizes itself after a storm, revealing patterns of equilibrium that would otherwise remain hidden. The light glows gently because the collisions are few and evenly spaced, producing a diffuse glow instead of a flashing display. This balance can last for hours before fading entirely. To the naked eye, it appears tranquil, yet the underlying physics remains immense. The quiet arc overhead is the visible edge of a vast electric river, a reminder that even the gentlest light can trace the shape of forces larger than imagination. Auroras have been seen on Mars from its ancient magnetic fields. Mars no longer has a global magnetic field like Earth's. but patches of magnetism still remain locked within its crust. When streams of solar particles strike those regions, faint auroras flicker in the thin Martian atmosphere. They appear as localized glows, scattered across the planet rather than forming a single polar oval. Spacecraft orbiting Mars have detected these flashes in ultraviolet light, invisible from the surface but rich in information. They reveal how the solar wind interacts with remnants of a once active planetary core. Each glow marks a place where ancient magnetism still lives, echoing a time when Mars may have been more like Earth, protected by a global field. The discovery of Martian auroras helps scientists piece together the story of its magnetic past and offers clues about how atmospheres evolve when their shields weaken and the light of the sun touches them directly. Even Venus shows aurora-like glows on its night side. Venus lacks a strong magnetic field, yet when intense bursts of solar wind strike its upper atmosphere, the dense air can still produce faint emissions of light. These glows occur on the planet's dark hemisphere, where charged particles collide with carbon dioxide and oxygen high above the clouds. Spacecraft have recorded flashes of green and ultraviolet light that pulse after powerful solar events, resembling auroras in both timing and cause. Because Venus's atmosphere is so thick, these lights never reach the surface, hidden beneath layers of swirling acid clouds. Scientists study them to understand how magnetic interactions can occur even without a global field, guided instead by electric currents in the ionosphere. The phenomenon shows that auroral processes are universal, shaped by energy and matter wherever they meet. Even a world wrapped in perpetual cloud carries traces of the same luminous dialogue between sun and planet. Studying alien auroras helps us understand distant worlds. When astronomers observe auroras on planets throughout the solar system, they glimpse the invisible threads that connect magnetic fields, atmospheres, and solar winds. Each planet offers a different experiment. Jupiter's immense field creates auroras so powerful they could vaporize spacecraft. Saturn's pulse in rhythm with its radio emissions. Mars and Venus reveal how auroras can survive even when magnetic shields fade. These observations teach scientists how stars influence the worlds that orbit them. The knowledge extends beyond our solar system to the study of exoplanets, where auroral signals might one day reveal atmospheres, magnetic strength, or even potential habitability. To read an aurora is to read the fingerprint of a planet's soul, the visible trace of how it meets its star. Across the cosmos, the same interplay of energy and air may shape lights that no human eyes will ever see, but that still shine in greeting. Aurora light travels for milliseconds but tells a billion-year story. The glow that appears above the poles lasts only as long as an atom remains excited, often less than 1,000th of a second. Yet the energy that makes it possible comes from a star born billions of years ago, still fusing hydrogen into helium deep within its core. The sunlight that warms the Earth and the solar wind that powers the aurora are both parts of that ancient process. Each flash of light in the sky is therefore a note in a song that began before life existed. It carries the story of cosmic creation, of matter forged in the hearts of older stars and now playing across the thin veil of our atmosphere. The timescale is impossible to grasp, yet the message is simple. Every spark above the poles connects the present moment to the birth of the universe, a brief shimmer linking eternity to now. Every aurora is the breath of the sun meeting the soul of Earth. The sun exhales streams of charged particles into space, and Earth receives them with a gentle, luminous reply. Between the two lies a relationship as old as the planet itself. Each display of the northern lights is an expression of that connection, a rhythm of giving and receiving written across the sky. The light curves and folds like breath made visible, while the ground below reflects its color in snow and sea. The spectacle is not merely energy or physics. It is the visible boundary of unity, where a living planet greets its star in beauty. To watch it is to witness a conversation between warmth and shelter, between the source of life and the world that it sustains. Every shimmer is a heartbeat in the long dialogue of creation, reminding us that even in the cold of night, we are illuminated by the fire that gave us birth. As the final light fades from the sky, imagine the aurora slowly dissolving into darkness. The air grows quiet again, and the world beneath it rests. Somewhere above, invisible currents still flow, whispering through the edge of space, carrying the last traces of energy from the sun's great breath. The same forces that create the aurora still hum within you, gentle and steady. You are made of the same atoms that glow in the northern night, born from ancient stars that once flared just as brightly. To watch the aurora is to remember that we belong to a vast and living cosmos, connected through light, motion, and time. If you enjoyed this quiet journey, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. Now let your breathing slow. Let the colors fade in your mind. Let the calm settle through you like falling snow. Good night.